think we can go ahead and get started. So on the webinar today, we will be talking about the science behind HydroForecast, which is our streamflow forecasting model. We're going to be talking about some of our latest feature updates, and also we'll discuss some of the upcoming work and improvements that we have planned. And for those of you who have not met Alden or I, we are from Upstream Tech. And for those of you who have not met me, my name is Alexandra. I'm the HydroForecast account manager, so I work with all of our HydroForecast customers. Alden is our chief technical officer, and he's also one of the co-founders of Upstream. And we're excited to talk about HydroForecast today. You can go ahead and hop to the next slide. Sweet. So just setting the stage before we jump into things. So Upstream Tech is a 30-person software company. Our team is made up of software engineers, machine learning specialists, hydrologists, water experts, and HydroForecast is one of Upstream's 2 products. So HydroForecast is our theory-guided machine learning model, which predicts stream flows, and it is used by hydropower producers, water utilities, governments. We have some examples, we are showing logos from some of the organizations that we partner with on the right side of the screen, and we currently are operational in 13 countries and across 5 continents, so we are expanding globally. And at Upstream, our mission is to make weather and water data actionable by delivering hydrologic modeling that's accurate, agile, and decision-oriented. And what are we going to talk about on the webinar today? So we will be giving a deep dive into how HydroForecast short-term works, which is one of our forecasting models, give a few examples of our short-term model in action, talk about our latest dashboard features, and then discuss some upcoming research and development. And then we'll save time for any questions. So just drop those into the Q&A box. So what is HydroForecast short-term, just to set the scene a bit? HydroForecast short-term is one of our 4 forecasting products alongside HydroForecast seasonal, HydroForecast extended seasonal, and HydroForecast long-term, which are our forecasting products that predict stream flow out longer horizons. HydroForecast short-term predicts hourly flow out to 10 days ahead, and we operationally are updating our forecasts every 2 hours. So whenever we set up a new forecast, we start with a core model that has been trained on over 500 basins, and then it is further tuned with local data to learn a specific area of interest. And we are here HydroForecast at Upstream and HydroForecast, we're continuously working on research and development, and we're rolling out new updates to all of our operational models periodically. And with HydroForecast short-term, our latest model version is what we call the distributed model, where we break up large basins into smaller subunits to capture spatial variation. And currently, it's the only deep learning distributed model that is operational. So on that note, I'm going to pass to Alden to give a bit more detail on how our distributed model works.
Thanks, Alexandra. All right, so I'll just focus a little bit on how the distributed model works under the hood, but starting back up a little bit higher, what is a distributed model? A distributed model is a river hydrology model that breaks a larger river basin into smaller subunits in order to account for the diverse hydrologic conditions across the larger basin and to account for the amount of time it takes for water to flow through the river network. So when we split up a very large basin into smaller subunits, this allows us to improve our forecast accuracy, particularly in shorter term hourly forecast predictions, where those changes really matter hour to hour, where the water fell and how long it's going to take to get down to the point that you care about. One other really nice benefit of a distributed model is it makes it possible to take advantage of stream flow gauges or other observations, on the ground observations that we have at particular points in the river network upstream of flow forecast points that our users care about. So for example, you might have a stream flow gauge, 18 hours upstream of you. In our distributed model, we can now take advantage of that information and be able to have an extra accurate forecast for those first 18 hours, because we can already see the water in the river and just have to understand how long it's going to take to get to you. So digging into a little bit how we go about setting up this distributed model, we start out by training what we call our core model. This model learns hydrology across hundreds of basins, and it is a neural network-based model. And the key thing here is that we train it over a diverse range of space and time, so it sees quite a bit of different and varied hydrologic conditions in terms of weather and what's going on the land. The inputs into this model are, as many of you know, are recent weather information and weather forecasts, satellite land surface observations. So those can tell us things about snow and vegetation that the physical science tells us are very important for hydrology. And then also basin characteristics. For example, how big is this basin? How steep is it? What's the elevation? What are the soils like there? And then the main predicted output is stream flow, how much water will be in the river at a certain point of interest. With the distributed model, the next step is then to break a larger basin up into these subunits. And we do that using spatial elevation data in order to find out where there will be confluences between rivers, and then also introduce additional breaks in different subbasins based on where there are stream flow gauge information or where our users want to have a forecast point, because we need to have an outlet of a subbasin in order to put a forecast point there. Then we take that core base model and we go do further training specific to the particular basin of interest. That we call this process tuning, and it's using, start out with that core model that we learned in the first step that has a general understanding of hydrology, and then provide it with further information specific to the particular basin that we are training in. We use all the same inputs as we used in the first step, but we can also take advantage at this point of particular gauge data from that basin, whether it be gauges that are internal inside the basin or at maybe the furthest downstream outlet point. We can also take advantage of known reservoir release information in order to start taking account of upstream regulation that may be happening at dams. And again, the output of that model is stream flow. And then the final step is we actually produce, once we've done that tuning process, we create predictions by producing and pre-processing time series for every single one of these subbasins that you see here, having the model predict how much water will be running off each of those subbasins into the river network, and then having the second part of the river model, which represents the river network itself, flow that water all the way through the river down to the points that we care about in the basin. So how does that particular flowing the river water through the basin work? The model, the way we have designed it, first looks at that digital elevation data, the spatial information about where rivers are going to flow, and represents the dependencies of what flows into what. And so it's representing the river basin as a graph, where there be nodes in that graph at the outlets of all the subbasins, and also at river confluence points or any stream flow gauges or forecast points that we care about. And then edges in that graph represent stream reaches, where water is flowing through. And the model begins by predicting stream flow at each of these subbasins. That goes into each of their respective nodes in that graph. And then it moves into the portion of the neural network, which actually represents the river network. And that is routing water through the basin, starting at the upstream most confluences and river reaches and working downwards, adding up flows as you get to confluences, delaying flows as they flow down a reach, adding up additional flows as you get to the next confluence, and so on and so forth until you get to the bottom. The way that it actually figures out flowing water down each specific reach is doing something called predicting a unit hydrograph. And that's just a fancy hydrology term for a description of how long it will take for water, like 1 unit of water that shows up somewhere, to arrive somewhere else. In our case, 1 unit of water that shows up at the top of the river reach to arrive down at the bottom of a particular river reach. And in our case, the model is predicting one of those unit hydrographs for every single hour at every single river reach. And the reason we do it at every single hour is because water flows at different speeds depending on how much water is in the river. And so this model is actually looking at how much water is in the river at the top of that river reach, in addition to what are the characteristics that it's learned about that particular river reach in terms of how long it is and how slow water takes to get through it, and then predicting, given that current flow rate and that river reach, how that water will show up down at the bottom of the reach. And finally, when we get to a node in this graph where we actually have on the ground streamflow observations, for example, there might be a streamflow gauge in the river, we'll actually take that information and replace any forecasted flows that have been flowing from upstream in that river. We'll replace those with the actual observations that that gauge has reported, and then allow that time series, which in the far future is comprised of a forecast coming from upstream, and then in the recent past is comprised of actual streamflow observations, will allow that whole connected time series to then continue flowing down through the river network. And that allows us to take really good advantage of real-time streamflow observations that are within the basin if they are available. That also allows us to incorporate scheduled releases from upstream regulated dams if that information is available. That can be sent to us, and then instead of a forecasted inflows that we predict that the model assumes will be then coming out of some dam, we actually have flowing out of that dam the schedule that has been provided to us. So this is not predicting what humans will do with their reservoirs, but it is allowing us to start to incorporate some of the very challenging problem of upstream human decision-making and regulation in river basins. So a couple examples of this in action. Where we see the largest, kind of qualitatively, where we see the largest improvements are during big, fast-moving streamflow events. For example, like this event here, which was in the Christmas of 2020 in the northeastern US. In many areas, it was a rain on snow event. Where there's some warm rain, a good amount of snow on the basin, but it was not consistently a rain on snow event. In some places it was, some places it fell as snow, some places it fell as rain on snow. And so this is a type of case where the differences within the basin are really important for the model to be able to see. And we saw really exciting results when we applied this distributed model in a couple different basins in the Northeast for this particular event. On the top here, you can see that the forecast really didn't get the peak how we would like it to be. I'm not satisfied with that forecast. And that's because it was just looking at the basin as one big average. So it couldn't see all the detail going on in different places in the basin. And then the distributed model was able to actually almost entirely nail the magnitude and timing of the peak, which is really exciting. We also, at a kind of more broader statistical evaluation of this model, have seen consistent accuracy improvements at all of our forecast horizons of the short-term model going out to 10 days into the future. This is just one example here. It's the Klein-Gupta efficiency. It's very similar to the Nash-Sutcliffe efficiency. Higher is better. And you can see these dark purple lines, that dark purple bar at all horizons is better than our previous model, which was already doing fairly good. So we're pretty excited about this, and I'd be happy to answer more questions about it in the Q&A. But for now, I'll hand it over to Alexandra to talk about some new features we have.
Awesome, thank you. So we have rolled out quite a few new dashboard features in the last few months. So we'll give an overview of some of those. One of our new dashboard features, I guess to start off, for those who are not very familiar with our dashboard, in addition to our flow forecasts, we display all of the weather inputs that are going into our model and are impacting our flow forecasts. One of those being precipitation and temperature. So one of our new features is we added the ability to view precipitation cumulatively in addition to as a rate. So we know a lot of our users are interested in knowing what is the volume of rain that is going to be falling within my basin in the next X amount of hours. So the cumulative option gives a really easy way to just see, oh, we're going to be getting 3 inches of rain in the next couple of hours, instead of calculating the area under the curve from the rate option. So that is one of the features we are very excited about. And hop on to the next slide. Along with the release of our new distributed model, one of our other new dashboard features is we added the ability to view weather inputs and surface observations and how they vary spatially across a given basin. So for our weather inputs for precipitation and temperature, we're showing daily averages and how those vary spatially over the next 10 days. And then for surface observations, we're showing vegetation, snow cover, and snow water equivalent and how those vary over the last year. So we're showing monthly averages, and we know it's helpful for a lot of folks to understand what area of my basin has the most amount of snow and what areas of my basin are going to contribute the most to snow melt or stream flow over the coming months. So this is a really easy way to quickly digest the current state of your basin and also how it's changing over time. And yeah, can hop over to the next slide. So one of the big features that we have been working on is forecast notifications. So of course, you can log into the HydroForecast web dashboard and view all of your flow forecasts and weather inputs, but we have recently added the ability to opt into daily digest emails. So if you head on over to the top right of the dashboard, hit settings and then notifications, you can toggle on the switch for either your 0Z or your 12Z initialization times. And those correspond to our 2 primary updates. So at those times, 0 UTC and 12 UTC, we are pulling in new weather data and we are issuing a new streamflow forecast. So if you sign up for either of those daily digest emails, we will send you an email once a day, just summarizing your short-term flow forecasts. So we send a tabulated a table with daily averages over the next 10 days. And the other form of notifications that we have recently released is the ability to opt into threshold-based alerts. So if there's a certain set threshold that might denote risk or action for your team, if a certain flow level means there's potential for downstream impacts or flooding, or if maybe there's a certain flow level where you can't fall beneath those flows because of some strict flow requirements, you can set a threshold and we will send you an email if our forecast is expected to exceed or fall below that set threshold. And you can actually set thresholds on any flow forecast or any weather inputs. And we are currently working on building out our forecast notifications to make them the most useful for all of our users. So we would be very happy to hear any insight about how your team thinks about or defines a significant event. We've heard from some users that folks think about flow increases or precipitation events in rate of change. So for example, 100 CFS per hour or a certain percent flow increase. So we'd love to hear about any ways that your team might define an event of interest. So please drop any thoughts in the Q&A box or reach out to us afterward, and we'd love to hear more about any ideas you have for notifications. Cool. So moving right along to some upcoming work and improvements that we have planned. So one of the items that we've heard from users is that many folks want access to the latest and most up-to-date weather data, both on the dashboard and to be incorporated into the streamflow forecasts. So I guess taking a step back, right now, the weather forecasts that we use in our model are 0 UTC and 12 UTC forecast initialization times from ECMWF, GEFS, and GFS. So at those 2 times 0 UTC and 12 UTC. Those are the two primary initialization times of our forecasts. And actually in between, as a side note, in between those two primary updates, we're actually updating our forecasts every 2 hours to incorporate and adjust our forecasts to the latest streamflow gauge observations that our model has pulled in. As Alden mentioned, our distributed model can pull in stream gauge observations from upstream basins, and also at, if we're receiving back calculated observations at the flow forecast point, it will also adjust to those. And in the future, some of the work we have planned is to incorporate additional weather sources such as HER, and also more frequent initialization times. So 6 UTC and 18 UTC initialization times from ECMWF, GEFS, and GFS. And yeah, pull in HER forecasts. And right now we're actually displaying some of these weather forecasts on our dashboard just as a first step to give users access to the latest weather data that's out there. And then we plan to incorporate all of these additional forecasts into our streamflow forecasts as well. Cool. We'll pass it back to Alden to talk about some of our other forecasting products.
Thanks, Alexandria. So a entirely new water prediction product of ours we recently launched this spring, which has been really exciting for the team to work on, and also I think a very interesting and useful new piece of information for our users is what we're calling HydroForecast long-term. So these are climate change informed water resource assessments for your basin. If the core output of this is daily stream flow values from the present out to 2100, and one of those for every single climate model, and then also a couple different methods of downscaling global climate models producing weather data at kind of a coarse resolution across the globe, downscaling those down to smaller grid sizes that actually cover your basins. There's a few different approaches you can take to that. So the result is that you get, for each emission scenario, so the climate models say, what if us humans really got our act together in terms of emissions and decided to really strongly invest in low carbon technologies for energy? What would the world look like under that scenario? Within that, there's about 20 different modeling centers, teams around the world, and they each have their own take, given that scenario, what they think would happen. And then within each of those, there's a few different downscaling methods about, so what would that global picture look like for your particular basin? And so the result is you get a wide kind of cone of traces for each emission scenario for your particular basin of stream flow at a daily level. And then we go about summarizing that and describing what those changes are at a slightly higher level. And that's something that we're going to be doing a lot more of, figuring out how to present this really exciting information and what questions it can help our users answer in a new grant, which we were recently awarded from the Department of Energy. It's a small business innovative research grant that came from the Water Power Technology Office there. And that's going to support further development and research into this long-term product, but it's actually already available at the moment. We've been very lucky recently in terms of getting small business innovative research grants. We also received it's currently pending small business innovative research grant from NOAA to further improve our seasonal forecasting product, HydroForecast Seasonal. As you all know, seasonal forecasting is an incredibly challenging problem, so there's always more work to be done there. With this award, we're going to be focusing on how do we get a better ensemble of weather information that we put into the seasonal hydrology model as we run it out into the future over the 90 or 370 days into the future that it runs. And there's a number of techniques that we're excited to try out for that. And another thing that we're going to experiment with is having the model not just predict stream flow, but also predict its estimate of what the snow water equivalent will be at each time in the future. We're going to do this for two reasons. One, because we've just heard from users that it's really exciting and useful to be able to see what the model thinks in terms of snow water equivalent and what it thinks it will be as you go through the next season, particularly in the spring when the snow is melting. And then we also, in our long-term work with this product, we found as we were developing this model that if we actually asked the model to predict both snow water equivalent and stream flow at the same time, we saw more reliable predictions of stream flow because we were asking the model to make sure you also got the snow water prediction correctly itself. It's not like our current models are not tracking snow, they are internally, but we were pretty excited to see like an even higher level of accuracy and reliability. So we think that is going to be an exciting improvement for our seasonal model, and it may also come to our short-term model as well. And finally, this is an area of very active research and development, and I mention it because we do not currently have a product around this, but we are seeing some interesting early results. And if it is something that piques interest from you as a potential user, I would love to hear more about what that interest is and what kind of questions it sparks. So this is definitely in the most R&D, not yet a product of all of the things we've mentioned in terms of upcoming work. But what it is a reservoir operations optimization tool that uses a particular branch of machine learning called reinforcement learning. And this is a type of machine learning that is really good at figuring out strategic, optimized solutions for problems that require long-term planning, essentially the type of like smarts and strategy that we usually attribute to humans. It has been used really famously to create the most successful Go, the board game Go, to create currently the best Go playing machine or human on the planet is using reinforcement learning. That was a team at Google who's done this. And the way it works is you create a simulation of the game or the environment or the real world, essentially like your digital twin. And then you have an agent, which is represented by a neural network, and you let that agent play or experiment in that simulation world for a very long time. And it gets feedback about how well it's doing in terms of, for example, in our case, how much electricity you're generating, how much revenue you're producing, how frequently you are doing things that we don't want it to do, like produce floods or violate, regulatory constraints. And after experimenting for a long time, ultimately becomes almost as optimal as possible given the current environment of producing reservoir schedules. Now, that said, our hypothesis with this is that there is no one perfect reservoir optimization. We don't want to just turn over our dams to reinforcement learning agents and have them run dams. We do not think that would be a good idea. The way we see this being used is a human is able to go in and actually adjust the relative weightings of different characteristics and constraints and priorities at that site for the particular moment in time that they're creating a schedule, and see what the optimal schedule would be under those different conditions, and see how much overlap or lack of overlap there is between those schedules, and ultimately be able to save and select a forecast that they like from the number of suggestions as they interact with the tool. So it's really a human in the loop being supported by this optimization agent. So that's I'd be happy to talk about all of this, but that's the kind of summary of the exciting new things that we've been working on lately. And we'll pause now, let some questions accumulate. I know there's been some really good questions I've seen come in so far. Again, feel free to open up that Q&A box to drop them in. And if you have additional questions afterwards, feel free to email them to team@upstream.tech or either of our email addresses that you see right there. So yeah, Alexandra.
Yeah, thank you everyone so much for attending. Please, yeah, as Halden mentioned, don't hesitate to reach out with any ideas, feedback, questions. We would love to hear from all of you. I see a few questions in the Q&A box so far. The first one is, what is your criteria for splitting the basins out into subbasins with the distributed model? So as Alden mentioned, we split out subbasins or subunits based on both spatial elevation data and also based on the availability of any upstream publicly available gauges upstream of our forecast point. So we can operationally use that gauge data in real time. Alden, do you want to give any more detail on the spatial elevation aspect?
Sure. Yeah, so we use kind of a modified existing algorithm, but there's lots of things to weigh here. Some other details are that we always make sure that each subbasin is less than 300 square kilometers, which sounds actually fairly large, but we found that as you go any smaller than that, the inaccuracies in spatially in the weather forecast information really start to dominate the errors in the source of errors in the ultimate streamflow prediction. And when in these particular neural network based models, we don't gain much from going any smaller than that. So I guess maybe the other things is that it's trying to basically balance having confluences that naturally are the outlet of some particular like logical river basin, while not having each of them too big or too large, and having roughly equal sizes of all the subbasins.
Awesome. Next question that I see in the Q&A box says, you captured the magnitude of the peak or timing of the peak. What is the priority of the model, catching the timing or the magnitude? I can say for starters that both are priorities of our model. And when we set up a model, we tune our model Cs while we're training it, historical inflow data, and we will train it to that. So it learns how the basin responds to different weather events, and it will learn, timing wise and magnitude wise, how the corresponding flows will respond to precipitation or different weather events. Alden, is there anything else you want to add?
Yeah. For the very mathy folks on the call, the objective function that we use to when training the runoff, the streamflow model, is we have it maximize the probability that the streamflow observation at every hour came from the predicted probability distribution. So it's predicting a probability distribution at every single hour, and we're asking it to maximize the probability that the observation came from the predicted distribution. And if you kind of dig into the math there, it ultimately ends up being very similar to a squared error. So small errors are not penalized very much. Very large errors, because they are squared, are penalized quite a bit. And so this penalizes the model both if it gets the magnitude wrong or if it gets the timing wrong. Both of those would be large squared errors, and then tell it to react and fix its predictions strongly.
Awesome. And I see just one more question in the Q&A box, and I also see a couple in the chat box that we will get to as well. But in the Q&A box, I see, what is the weight of roughness in your routing module for calibration? Does the model consider changing roughness or infiltration parameters? I assume it plays with roughness for timing and a mix of roughness and infiltration for magnitude. I'll pass this one over to Alden.
Sure. Yeah, so the set of information that we provide to the model as it's predicting the flow delays at each reach, as it's predicting those unit hydrograph parameters, is something that we're working on pretty actively right now. At the moment, what we provide is actually just a identifier that says this is reach number 22 or this is reach number 12. And the model learns by looking at past data about what the timings of flows down that particular reach are that are unique to that one specific reach. So there's some pluses and minuses to this. Some alternatives that we can try out are putting in kind of general information like the length or the sinuosity and the average slope and maybe roughness or other infiltration parameters along the way. That would allow us to produce a general model, where that routing delay, what is learned about that, is applicable to totally new locations where we never have seen before. The benefit of doing it with the identifier is that it allows it to really dial in to that particular reach and say there's something interesting going on there, like maybe a very, very tiny dam that slows water a little bit, or some sort of withdrawals along that stream reach for maybe agriculture or development. The model's able to learn that as well. So the short answer is that's that component about what information we actually provide is something we're still working on.
Alrighty, and then I just see a few more in the chat box. Thanks for sharing the work. It's amazing. Thank you. We're happy to hear that. First question is, do we consider big lakes when you split subbasins? Alden, I might pass these ones to you.
Yeah. That's not something that's explicitly required in the current algorithm. However, it's also very possible for us to just tell it, you should break here or here or here. And often there are streamflow gauges right at the outlets of lakes. So we will often, just because of the locations of observations, end up splitting at an outlet of a lake. Having something like a lake in there is actually not an issue for learning the timing and delays of flows, like I was describing, by just saying this is reach number 34, because the model can see, I see that this particular reach behaves a little bit differently. Probably the water flows through it maybe a little slower. It might not know that that was because it was a lake, but it can still learn how it actually works and then produce strong predictions.
Cool. And then the last question that I see, also a great question, so please feel free to ask more if you have any, is how do we obtain the parameter of the unit hydrograph using the machine learning approach?
Great question. Great question. So this is really getting down into the nitty gritty of things. So if this doesn't make sense, don't worry about it. But what we predict at each reach is 3 parameters. One, the mean of a normal distribution, so the average time that it takes flow to flow down this reach. We also predict the standard deviation, so that's describing how much water, a unit of water, will spread out in time as it flows down this river reach. And then the third parameter we predict is a volume gain or loss, which defaults to maintaining volume. But it can learn that, for example, this reach is losing or gaining because of maybe some water withdrawals along the way that we don't necessarily have explicit information about, but the model could back out. So how that actually happens is at every time step, there is a relatively small subcomponent of the neural network, and it's looking at information about the reach, so that identifier, as well as the stream flow rate at the top of that reach. And it's going through a small feed-forward subcomponent of the neural network and predicting those 3 parameters that come out of it. So that's how it, and in that process, those values are, and that subcomponent of the network is learned at the same time as we're learning the entire rest of the neural network in that process where we're tuning it to a particular local basin. I also saw a question about, do we have a preprint for this work to read? And the answer is not yet, but we will. Keep an eye either on our, you're probably on this, if you're on this webinar, you're probably on our newsletter. Keep an eye for that, or on our website in on our Explore area. We post our research there. Great
Awesome.
questions.
Yeah, great questions. Those are the last of the questions I see. I see a couple of comments. Great cumulative function and the reservoir operation product is very cool. We're happy to chat about any of the upcoming work or any of the features if any of you would like to chat further or have any thoughts or ideas on those or more questions. Yeah, if there are no more questions, then thank you all so much again for attending, and please feel free to reach out to either team@hydroforecast.com or either of our personal emails on the screen. But thanks again.